Hello. In this video, we are basically looking at our notes about the differences between linear equations and functions and exponential equations and functions. So from our reading, we define a linear function by a constant rate of change, and we saw that in the first example that we did. And then it has a slope-intercept form as well as the standard form, but the most useful for us is the slope-intercept form of the equation, which you do want to commit to memory as y equals mx plus b. Sometimes the equations are given in function notation, so the y value is replaced with the notation f of x, and it has the same meaning as the y or the output. In this equation, the m is where you put the rate of change, which can also be called the slope. The b stands for the initial value. The x variable is the input or independent variable, and the output or dependent variable is y or f of x. When you are graphing, we refer to the rate of change as the slope because it describes the slant of the line. And when we are graphing, we refer to the b value as the vertical or y-intercept. There are three different ways that you can understand slope. So in words, we have the change in the output over the change in the input, and this is sometimes simplified to the graphing concept of the rise. The output is the up and down on the coordinate plane over the run, the left-right movement on the coordinate plane. Symbol-wise, we can use the delta, like we had used for percent change, but here it would be the change in the y value divided by the change in the x value. When we look at a formula to figure out change, you do subtraction. And so we use the subscripts to denote that we must do the subtraction in the same order. So we use y2, the second y value, and subtract out the first one, divided by x2, so the second x value, and subtract out the first x value. We see an example, and it says in this example that the population of a city increased from 23,400 to 27,800 between 2008 and 2012. So we can use an intuitive approach to this. How much did the population change? Well, I did subtraction, as you can see here, and got 4,400. And that happened over 4 years because I understood from 2008 to 2012 is 4 years. And so I have in words, it changed by 4,400 people over 4 years. Putting that into the slope notation, the change in the y value is the 4,400 people divided by the change in x, the 4 years, or 1,100 people per year. If I want to show the formula, the y, the population, is based on the time. So the time is our x value. This would be our x1, and this happening later would be x2. Matching them up, the 23,000 number would be our y1, and the 27,000 number our y2. So putting that into the slope formula, I would take 27,800 and minus 23,400. And in the denominator, I would take the x2 first, so 2012 minus 2008. And you can see that I can set it up. I do each of those subtractions, which takes me right to the formula, the fraction that we had before as the answers, and gets us to the slope. So next, I wanted us to put together all of the different pieces that we had in our notes into a visual. So we have y equals mx plus b. And the things that we know that b is the starting value. We can also refer to that as the initial value. We know that m is the slope or the constant rate of change. We know that x is our input variable. It is not always, but it is often time. And that was the case in the example we just looked at where the time was in years. And then we know that y is our output variable. We can also think of this just as the value. And then we are asked here, what is the slope formula? So you definitely should know the slope formula. So we typically write this as m equals, and you can memorize it as rise over run. That is most useful in graphing, which we are not doing a lot of. You can memorize it as change in y over change in x using the delta for change. And again, that's a great concept, but you need to know the details. So you probably want to learn the slope formula as y2 minus y1 over x2 minus x1. So let's take a look also at exponential functions. So linear has the constant rate of change. Exponential increases by the same percentage. And so we saw this in the second example, that was a decrease, but it was the same percentage. So when we talk about percent change, it is changed based on the percent of the original. And we have this formula here, which you should know from earlier in the course, with the new minus old divided by the old times 100. When we have exponential growth, that is when you have a percent increase. And when we have exponential decay, that is when we have the percent decrease. When we look at this particular growth formula, the A is the initial value, the B is referred to as the growth factor, and then the X was typically the time. That growth factor is calculated as 1 plus the percent as a decimal. So those are our notes, and we have some additional examples. So this first part here, we already went over. Second part is the example. So matching this up with the model. So in the position of the A is the 125 or 1.25. So that's the initial population. In the position of the B, which is the growth factor, is this 1.012. So this is 1 plus the percent as a decimal. So that would be calculated by taking 1 plus the 1.2% mentioned here and dividing it by 100. And so when you do that, that's how you get this growth factor. The 18, the exponent up here, is the time. So in this problem, we would look from 2013 to 2031. That is 18 years. And that's where we got the time of 18, which goes in for the X in the original problem. So taking the formula that they gave us and just putting all the details in it. So they used A as the start. We're going to use P as the start, which is another commonly done notation. Just different authors use different notations. So here, P is our starting value, and that's the same position as our notes had the A. And then inside the parentheses, we have 1 plus R. R represents a percent as a decimal. And so that's how you get that growth factor that our notes had as B. And key in thinking of this is that it could be positive or negative. So if it's positive, you would add that percentage. And if it's negative, you would end up subtracting. So if it's positive, you have exponential growth, and if it's negative, then you have exponential decay. T here is our input variable. And since it's input, this is oftentimes an X. But the reason why T is used in this model is because, as we mentioned before, it is usually time. because growth or decay happens over a time period. And then the y is our output variable. And our output variable is often going to be the value in the problem. So like, what is the value of this? What is the value of that? How many people? How much disease? What value? So it will be important when we're working with data to have the percent change formula. So we did memorize percent change formula, which is new minus old divided by old. And then typically we multiplied by 100 to get that to be a percentage. But truly for percent change, for exponential growth problems, we don't want the percentage, we want the decimal. So if we just do this part and don't multiply by 100, that will give us the decimal for the percent change. So those are our notes that we're going to work with, and please make sure that you have good images of those notes in front of you so that you truly can work with them and you can apply them to the problems that we're going to be solving.